Hi there, in this short video I'm going to be making caged ball bearings. If you don't know, I make wicked awesome pocket knives and the pivot rolls on caged ball bearings. Now the problem with ones that you can buy online is that almost every single one uses steel ball bearings. And I don't like that because steel has the potential to rust over time, and for something that's relatively hard use like a knife, it might see salt water, whatever, harsh environments, the potential for them to rust is real, and you just don't want that to happen. So stainless steel or even ceramic ball bearings is a much better choice. Now of course you could buy these, you could punch out all the bearings and replace them with stainless or ceramic. Very doable. But my other problem with these is that the balls are 93 thou thick, and that's way more than I want. I want to build a pivot bearing that uses 1/16 ball bearings so that it's very compact, very tight. My knives are quite relatively thin, and to stick a ball bearing in either side of the blade doesn't leave a lot of room for the metal, both the titanium and the blade steel, to be thick and strong. And the thicker and stronger they are, the stronger the knife will be. So the smaller the bearing, the more meat you got. Here's a close-up of other ball bearings that you can buy online. Here are a few different variations of caged ball bearings that you can buy from stores. On the left, you have one meant for an 1/8" pivot with 1/16" balls. Very good bearing, but 1/8" pivot is very small. I got that from alphanifesupply.com. In the second left, it uses 0.78 balls, and the middle is, I think, just over 1/4 inch or just under 1/4 inch or so. So it's very, very sloppy on a 3/16 pivot, and I don't like that. I got those from another knife maker who I think sourced them custom. The blue one uses 93 thou balls, also from Alpha Knife Supply. It's great as a 3/16 pivot. The center bore is a good fit on 3/16. It's a very good bearing, although the balls are huge. And I make very thin folders, relatively, and it's quite a tight fit to get those big balls in there while still keeping, everything strong. So I want to use something with a 1/16 ball. And then on the far right is a roller bearing. I found that those tend to drag a lot. I haven't tried them in quite a long time, but because of the more contact area with all the rollers, it doesn't roll as smoothly and as effortlessly as the ball bearings do, because the ball bearings use such a small contact point, just the very tip of the ball. Food for thought, I got that one from vxb.com, a good online bearing store to keep in your back pocket. Now those ball bearings are great for their intended purpose, and a lot of knife makers use them, especially this blue one. My first 2 batches of knives used this blue one, and it worked fine. But I'm trying to increase the precision and the strength of my knife in any way that I can, so using smaller ball bearings is one of the ways that I'm going to do that. Now how, you may ask, am I going to make a cage like that? Well, I'm going to take a sheet of nylon like this. This is about 48 thousandths of an inch thick, and I'll be using balls that are 62 thousandths of an inch. So the sheet is obviously thinner than the ball, so that the ball sticks out on either end of the cage. Now, it's very tricky to machine something this small out of a big sheet without it flying all over the place. Here are some of my original tests. Now, I was using a regular end mill meant for cutting steel, and it left a very poor surface finish in the plastic. It just, lots of burrs and lots of ugly junk. So I ended up going online and buying these Kyocera end mills from an eBay store. I think his name was Drillman1, something close to that. They are single flute end mills meant for cutting plastic and aluminum. So as you can see, it's just got literally one single flute. I got 2 different sizes. The yellow ones are 1/16 inch and the green ones are 39 thousandths, which I think is a metric equivalent. And these are supposed to be the bomb diggity for cutting plastic. Let's check out my fixture. So in order to cut these bearings fairly quickly and reliably and accurately and in a grid, like doing a lot of them at one time, I made a dedicated fixture for this. I like my fixtures, and this is completely over the top and wicked awesome. So this is my Mighty Bite Vac Magic vacuum pallet system. Now, the majority of the time I use it as a pallet changer. All these pallets just come off for placements. I got a blades pallet here, I got other pallets there. They don't actually need vacuum to go through them. The plate is totally solid. It just sucks down onto the fixture, and it's a very quick pallet changer. I love it as a pallet changer. As a vacuum sucker, it works really awesome too, with the right sort of scenario. So, I have their 1/8 inch gasket around here. I machined a groove, which took forever with the 1/16 end mill. And then I machined O-ring grooves for each individual bearing, which also took forever. And then all these X's and cross patterns are to get vacuum on the flat areas of the sheet. So when I suck a sheet down, vacuum gets in all these little grooves and gives it just more surface area to suck down with. So each hole is threaded in the middle. That way, I can put my big sheet on here, I can drill the holes, I can profile it, or I can cut the pivot hole, and then I can stick a bolt through the middle and then profile around the outside so that the bearing doesn't go flying when it breaks through. And this round O-ring keeps vacuum out of the hole. So this little hole here has no vacuum force within it. All the vacuum is outside of the round O-rings. But that way when I punch through, I'm not losing vacuum because the O-ring keeps vacuum out of the hole and just on the outside. So I can punch through and it still works. In theory anyway. I haven't actually made one yet with this setup. One of the trickiest things is to get the ball bearings inside the cage. You can't just have a straight through hole, otherwise they fall out. Or they press in and then don't move. So the inside of the hole has to actually be conical on either side. You can't really do that with normal end mills. So I had to order a very special undercutting ball end mill from Harvey Tool. That's called Tool 7, I believe. Now this little guy, oops. Now this little guy is incredibly delicate and scary. The ball diameter is about 40 thousandths of an inch, and the neck diameter is 20 something thousandths of an inch. I'm afraid to break this thing just by touching it. However, it's a very cool custom end mill, and I like cool custom end mills. So I bought 2 of them, which is probably not going to be enough because I know I'm going to end up breaking one or both of them just through stupid mistakes. So I'm being as careful as I can. What else? So yeah, it's a 270 degree undercutting end mill, which means it's basically a ball 270 degrees around. This little end mill is about 10 times more expensive as a regular straight flute end mill of the similar size. So you really don't want to go through a lot of them. You don't want to break them. But anyway, what the undercutting ball will do is it'll spiral down and create the conical walls of the hole. So let's do some dry cutting, and then you can actually see the tool paths and how they interact and how they're supposed to go. So the first tool, I've turned the spindle off. Obviously the tool would be spinning. That's my 39 thou end mill, and it's cutting the bearing pockets for each individual ball, cutting them to an exact diameter so that the undercutting end mill can go in there and clean them up and make them conical. Okay, here comes the undercutting ball. So So it's actually spiraling down about a thousandth of an inch every revolution. Next up is my 1/16 inch single flute end mill. It's going to cut the inside pivot hole and the outside perimeter, the profile pass. Except I messed it up. So this is my 1/16 inch single flute end mill. Right now it's cutting the inside pocket for the bearing, or for the pivot hole. Rough pass and finish pass. And it moved up way high to give me a pause, and then I can go in here and thread in a bolt so that the bearing doesn't go flying when I cut out the outside. So after the pause, it comes back down again and then starts the profile. So that is how I will be using this fixture to machine a whole ton of bearings out of this. So like I said, I haven't actually machined any yet. I've just done some air cutting like that. But so far I'm really happy with how it's turning out. I think it's going to work great. And I like this method because I can really tweak the tolerances and the dimensions and the conical clearance for every ball and the, everything. The pivot hole diameter. I can make them exactly how I want them to fit my knife perfectly. What I like about doing it this way is that with some creative fixturing like I got there, I can do a fairly large area. I can do 56 bearings on that one sheet, and I can do 3 of those chunks in one sheet of plastic. And these are relatively cheap, but the machine time and all the figuring out took me a lot of time, so that's what you're paying for in a store-bought bearing. But the fact that I get to tweak all the tolerances and dimensions and make them exactly do what I need them to do is pretty cool. And if I can ever find this material in some crazy hot pink or yellow or something like that, then I might do that, because just to stand it out as my own, obviously made by me. So what else? Now in this video I basically just described exactly how I do it, and that took me a long time to figure out. So I'm sort of just going out on a limb and, taking the risk of explaining how I do it and showing everybody how I do it. But I honestly don't think anybody's going to copy me, because this is really complicated. And store-bought bearings are, they're a couple bucks each. Whereas all this time I've spent a lot of time and development and materials and making that fixture, and hours of figuring it out, and fixture making, and testing, and broken end mills and custom end mills and all that stuff. It's very expensive and it adds up a lot. Yeah, I tend to do that. I tend to dive into projects that are way bigger and more complicated than they need to be, than they should be, and that I probably shouldn't be taking on in the first place because I'm crazy busy with everything else. But I find them really challenging and really interesting. And that's what I love about machining, is you can, you see an idea online or in a video or in a store or something like that, and you're like, one day I gotta try that idea. It's gonna drive me nuts if I don't try it. And this has been a combination of, cool spiral, conical pattern, toolpath with vacuum, O-rings, and tight tolerances, and just getting everything to work right, and using single flute end mills. I don't know, all these things just really geek me out and make me excited. That's the thing with machining, is I love machining, and I think it's the coolest thing ever. And manufacturing technology and all that, I just think it's amazing. I love knives too, but I actually think I like machining a little bit more. And being able to do both at the same time for the same business is pretty much the coolest job ever for me. you know, with 2 kids and job at home, and it's crazy, crazy busy. I don't get to sleep till 4 a.m. every night, but it's completely worth it because I'm super happy doing what I'm doing. Now here's hoping that the bearings actually work out, and let's find out. So on my fixture here, big O-ring on the outside keeps most of the vacuum, all the vacuum within that O-ring. So I've got my sheet of plastic here. I'll line it up sort of with the outside, make sure it covers the O-ring completely and is relatively centered. And then because the plastic is kind of warped and bowed, it's sometimes hard to get it going, but I'll turn the vacuum on. And then I have this big plate to help suck it down. And then I can hear that it's actually sucked properly. And I have a vacuum gauge right there that I can verify. It's pulling about 24 inches of vacuum. Perfect. So now I can take this guy off. And then I'm ready to start machining. I mean, this thing is not going anywhere. If I lift it up, I can pop it off. But that's lifting it up with, you know, 8 inches of leverage here, and it's just arcing it up. But as far as side loads and individual toolpath pulling up loads, it's very stable. Wow, what timing. The first hole that I filmed, and it breaks. Fun. So that single flute end mill left a very crisp edge on the bottom. Pretty nice burrs on the top on all edges. I think I might be feeding too slow. Maybe if you feed a lot faster, it'll get rid of those burrs. I'll need to do either some experimentation or some research to figure out what's going on there. But anyway, that is my bearing. I'll shove 10 stainless steel balls in there and then see if it works. Super happy so far. This is the process, you know, trial and error, practice, 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 tweak, practice again, and then you finally get something that's production ready and you can make thousands of them. And that's the goal, you know. All this work to make 2 bearings would not be worth it, but I want to make, you know, hundreds. So it will be worth it. So the tolerances on that bearing were a little bit too tight. I need to open up those conical areas and tweak them a tiny little bit. You basically want the balls to be able to rattle inside there if you listen real close, and they're too tight right now. But kind of does the job. Very happy with how that's turning out, and the next ones are going to be even better. So that is how I'm going to be making bearings. Do I have to make my own bearings? No. Do I want to? Mm-hmm. Super cool, awesome wickedness. Mission accomplished. They're perfect. They slide really good. And if this is any indication, just a steel or aluminum block on aluminum block. Yeah, they work great. Perfect. And I got those burrs out. No problem. Just tweaked a bunch of stuff, added some things, and now directly off the machine they require 0 hand finishing, except stuffing those balls in. And it just works perfectly. They take longer than I thought they would originally, to the point where it's almost not cost effective to make your own, but the accuracy and precision with which these are made is just absolutely perfect, and I like that. So I'm actually really happy that I'm making my own now and can make them exactly how I want them to make. And they work just flawlessly. Now to make tons more. Thanks for watching, guys. Bye.